In numeral geology, scale and resolution play different but closely connected role. Scale, whether we're looking at the crust, reservoir, or an outcrop, defines a physical extent of the system we're modeling. Resolution, on the other hand, controls how finely geological features such as faults, faces, fractures are represented, typically through grid size or model detail. High resolution allows us to capture geological heterogeneity, like thin layers or subtle structural features, which can be critical for understanding fluid flow or reservoir behavior. At the same time, higher resolution comes with significant computational cost. That's why upscaling is often necessary, moving from very detailed models to coarser, more manageable ones that are still practical for large-scale simulations, resource management, or hazard assessment. This graph illustrates how scale varies across geoscientific and engineering applications. The dataset spans an enormous range from measurement on the other order of tens of thousands of feet down to micrometers. On the far left, the seismic stack operates at the largest scale, and at this level, certain types of variations such as fine vertical detail are necessarily averaged out. Moving to a smaller scale, the well log shown next is able to capture these vertical variations because it operates at much finer resolution. Going even further, thin sections reveal details within individual strata that are only visible at this very fine scale. Each dataset adds a different layer of understanding, but only within its own scale window. And the same principle applies to geophysical data interpretation. Scale and context must always be considered. This means understanding the spatial and temporal limits of each dataset and relating them to geological processes and models we're trying to interpret. For example, seismic data can vary widely in resolution and frequency depending on wave velocity and wavelength. Gravity and magnetic data have different sensitivities and level of ambiguity depending on the distance and orientation of the sources. Electrical and electromagnetic methods differ in penetration depths and complexity based on subsurface resistivity and conductivity. Because of this, it's essential to match scale with the right interpretation tools and techniques. And when scale, resolution, and method are properly aligned, the results are far more reliable and meaningful.